It just powered off.
Let me just try to get this thing. All right, so this homework, the last this one I never went through, and I just graded it and graded it. So what was this about? Yeah, it's the networks, the plus and minus network thing. And then so a couple groups, I think two groups didn't do it. I don't know if they're going to turn it in later or something. Anyway, and then one group got a 50. I think they didn't do, I mean, it wasn't, I just kind of graded it, and then the others, everyone else got like an A, I think. So anyway, it's the thing where you have the, let's say, I guess, is this a it's not a co-network. He's doing a simulation. He has two kinds of components in it, like A and B, I think he calls them. And then, let's see. First part, so I'm going to talk about scattering for like 2 lectures. So I'll talk about this art. Basically, what he does is so S is the intensity. Like if you had you had two polymers mixed, right? So they integrate each other. So the scattering from that. So what he does is he says, well, I could take one polymer and the other polymer, scattering from that one and that one, and add them together, right? But it turns out that isn't how things work, and I'll kind of drive how you get this equation. Basically, when things penetrate each other, you need to do this inverse sum. So you get a different answer. So I think everybody figured out that you get quite a bit different answer when you do it this way versus a straight sum. Again, like I'll go through like where that comes from. So anyway, everyone got that one right, I think. Except maybe the one group that got 52. Maybe they might have messed it up a little bit. I think they said that, I think that group said the opposite, that this would give you something got it backwards in that answer. Anyway, so so this is the thing. So it's basically I just wanted you to reiterate the thing that's in the notes from this business, right? So everyone kind of did that. I mean, most people did that. So you get the R is going to be 3/5 power to this blob size, and then the constant C star is going to be the 4/5. So you end up with this sum here, right? So anyway, and then the question is like, so this 3/5 means it's a good solvent, self-avoiding polymer, like it's in a good solvent. So it'd be 2 if it was a theta solvent, right? And then if it's a branched polymer, so again, let me just grab this thing. If we also refresh it. Yeah. Right, we definitely have the pen in it, but I just got in like a midnight, so it's just like kind of strong. Well, so we have the dimension is 5/3 for good solvent. We need to read this. Auto. Just moving around. How about, right. And then for then it's 2, right? So, all right. So, and then I also said that like the, I mean, at some point I said you could say it's like this connectivity dimension times the minimum dimensions. If you have something like this or whatever, like that. Right? So say the chains themselves are this. So that if you take, so D min is that if you darken like a path, like one side to the other conductive path through the thing. And then what's the dimension of that? So this would be like DF, that would be DF if it was within your chain. And C is like how branched it is. So these things are branched. So the DF, so, and sometimes people like 2.5 for a theta chain randomly branched. That's kind of like a number that people say like DF would be 2.5. If it's a theta chain, I mean that D min is like 1.25, but C is 1.25 for that case. So say you have, say radiation cross-link polyethylene would be sometimes. X-rays and it randomly pops off hydrogens, and they bond to the disproportionation, I think they call it, of the hydrogens, and they bond to the other chains. It makes a random branching, and the dimension of that chain ends up being 2.5. Right, so this business of the minus 3.34 thing has to be modified for this branching not being different. So say it's the same 5/3, so you still have that the R goes with the N to the 3/5, right? So that's when you have this thing is R times C over C star. So this changes. So like this R thing changes. So the C star number is still C star also changes. So anyway, when the dimension, so you have to kind of, this is, no one got this. The dimension changes when you have a branch chain. That's the point, because DF is the density. It's like the density. So if you say you have a random walk chain, well, throw in other chains on top of it that are the same random walk, it's got to be denser. So DF has to go up, right? Because you have more stuff there. So it's got to be a higher dimension. So the C number would go up by some amount that would raise DF total. So say if you have DF of 2, then I think this 3, you can work out what the 3/5 does in the case. So you have, see if I can get back here. I should be coherently do this. So C star is N, so N was N by, let's see, K and oh, R is 3/5, right? So you'd have to make, say it was 2, then it would be R would be N to the 1/2 instead. So it'd be 1 minus 3/2, right? Whatever that ends up being, minus 1/2, I guess, minus 0.5. Right, so C star would be minus 0.5 instead of minus 4/5, right? And then so you put that into this. So it wouldn't be 4/5, it would be 1/2 or 2.5/5 or whatever. But this wouldn't be 3/5 either. That would be 2. That'd be 1/2. So you'd end up with 3/5 goes to 1/2, and then the other one goes to also to 1/2. P 1/2 plus. So you end up with P. You end up with just P, I guess, in that case. So you get a different. If you get a different fractal dimension, both C star and the scaling C star and the scaling of R change, then this thing changes. And the way it changes is exactly how he shows. In other words, he doesn't say that in the paper. Basically, once you include the dimensional changes due to the cross-linking, then you get this shift in the slope. Instead of being 3/4 slope, 0.75, you get something steeper with the higher dimension. right? And that's exactly what he sees. So basically, he could have gotten the fractal dimension from this plot instead of just saying it's some number bigger, if you wanted to do it, right? And then because that's larger, so when you also when you get to larger and larger chains, then they collapse onto the same line, right? Because then you don't have the branching effect gets diluted. So the C number, C times dmin, the C would go towards one as a chains get longer between crosses, you're diluting the cross links. Anyway, so that's what he sees. That's kind of what he sees wherever he does that end plot. And then at that point they have to match up. At that point, the blob size has to match up, right? They all have to collapse under the same number out here. Once you get to such a large n, where is the n one? That's concentration. I thought there was one that's like n. It's a question on the thing, right? Anyway, when you get to long chains, then that dimension falls under. So they have to be the same at the high end. So if you extrapolate back and you have a steeper slope, you have to have a larger blob size when you have a higher dimension. And because you have a larger blob size, so blob size is where this thing tails over, right? So it has to, this is one over size. If it gets larger, it has to move to the left. And then, so that's why the curves are different, you know, it's basically because of that. If you did that analysis right, that's why the curves are different. Because topologically, the more branched one is going to have a larger blob size. It has to. So if they're the same at large n, at small n, it has to have a larger blob size. So anyway, he doesn't mention that. It's kind of in there. Anyway, no one said that, kind of obviously, but that seems to be the way this thing goes. That's the interesting part of this quiz, this homework, I think. Anyway, then like why do they show different scatterings? Basically because that top, when they're branched, they have a larger C dimension, connectivity dimension. Then clustering, everybody got that. And then people figured out that this is like the density number, or you can figure it out from the equations he gives in the, this is a power law for the density as a function of the mass. And we kind of did that with C, basically the C star scaling. And then this one, everybody kind of got the thing about his large scale. Oh, could the thing predict for large scale? So I think he doesn't mention that either. But anyway, so anyway, hopefully that's okay. It's kind of a while ago. It was like 2 weeks ago we did this thing. I just graded it, so it's a little bit fresher in my mind. But anyway, any questions on that thing? It does have to do with, if you work it right, it does have to do with what I said in class, you know. So anyway, then let's see. This is the swelling things. Then so this week's is on Casey's paper. No, let's see. What are these? Here. So it's a paper about mixing the ultra high molecular weight with a high density polyethylene. This is beeping at me. Check my rings. Always does something. Anyway, all right, that's good. So any questions on this thing? Let's see what the different kinds of mixing. So that's in the this Tadmore book, page 322, if you go there. I like this book. It's a book I picked up when I was kind of, so anyway, I have memories of it. It's kind of like, it might not be the best book in processing. but I'm fond of it. But anyway, he's got a chapter on mixing. Most processing books don't mention mixing, but it's probably the most important thing you do. Like everybody mixes stuff. So anyway, so he goes through a lot about. I like it because he does like a scientific perspective on how you would analyze mixing, kind of what numbers talk about for dispersion. He also talks about this distinction between distributive mixing and dispersive mixing. So basically, and he shows some pictures of that in here somewhere. So one is kind of a diffusive mixing, and the other's actually like mixing particles type thing. Someone here shows the picture. It's pretty good. I haven't luck with finding things. Those are he shows cross sections in an extruder. It's kind of interesting, and how you get this dispersive and distributed mixing in it. I guess that business would be at the beginning of this chapter, but I don't see it. Oops, wrong chapter. It's like 262. Yeah, no, it's in the place where it's something. There's what did I say? 322. Uh, 164. Oh, stop. That was the picture I wanted. Not that. Maybe it doesn't give that picture. It's basically a block picture like that other one. Just shows that in distributed mixing, you have the black and white, and then you break them into pieces. And just dispersive mixing, kind of smear them out, basically. So you get a gray. In other words, you go from black and white to all gray eventually with dispersive. With distributive, you break the blocks into small pieces, move them apart. Somewhere, that's from his book, so it's in there somewhere. But anyway, so you should be able to find that. That's what this question's about. It's like part of this is about what's the difference between dispersive and distributive, and then how does that relate to laminar flow? So I showed you laminar flow can be reversed. So you can't reverse this distributive mixing, you could reverse. Dispersive mixing, you can't. Because one of them is like a diffusion thing. You can't undo diffusion, right? So thermally wandering around, you can't go back. You can't go back to where you came from. Right? But if you actually move the pieces around, you can put the Humpty Dumpty back together kind of thing, especially with laminar flow, which is reversible. And then the high shear mixers are supposed to be going to more distributive mixing, like so basically if you're getting a lot more turbulence, you move the pieces around more, right? And then so he's talking about using, so there's a question here about what kind of mixing do you want when you have like long chains and short chains of the same polymer type. And he says in the paper that because of the same type, then they're miscible, which kind of makes sense, but the fact is that like if you take the reason why polyethylene waste is a big problem is that when you have like linear low density polyethylene, low density polyethylene, high density polyethylene, even different grades of high density polyethylene, that none of them mix with each other. So you can't make a blend of polyethylenes normally, so he says that they mix. All right, and in this case, he's using high density polyethylene, which is like the classic case. So linear low density polyethylene has these like regular like octene. So it's like 4 carbon. So it has 2 carbons for I guess there's 6 carbons on the side for an octene. right? So there's 2 carbons in the chain and 6 out the side, so it makes 8. Then you have regular spacing of those on the chain, and then so the crystals are going to go like that. These things have to stick out the side, so it fixes the crystal thickness, and it also, since the thickness of the crystal is proportional to kind of 1 over the melting temperature, so so that's going to change the melting point of the polymer. So if you can control the branching that way using special catalysts, you can control the melting point of the polymer and control the properties. Like you can also control the degree of crystallinity, right? So, and low density means low crystallinity. And then low density polyethylene is like the original polyethylene is just like a complete mesh of kind of branched things. So like a shotgun polyethylene. So it's got a lot of branches in it. And high density polyethylene is long chains with long chain branches on it. So in low density, these are short chain branches. In linear low density, they're short chain branches, meaning like 4 carbons of a branch. In high density, there's these long chain branches, so you can't distinguish between the main chain and the branch chain. And it's just kind of like an error happens in the polymerization, but it keeps going on its merry way, right? So then his polyethylene is going to be this like to infinity and beyond type of thing. It's just going to keep going. This is some huge polymer. I forget what we said it was, like 16 times longer. So anyway, so he says originally, like they're going to mix because they're all like CH2, and that's it. But the fact is, like, none of these things mix. None of them, yeah. Oh yeah, sorry. I can figure out how to do it.
It might have to zoom in just a little bit, maybe. Or top focus, I guess. Oh, that's good.
That's okay. Zoom or something.
Just continue that, just so it doesn't focus. Sometimes it will focus on your sleeve.
I
Sometimes.
see. All right. So yeah, it's still. I should just take
Yeah,
off.
it was
If I knew how to turn off autofocus. Anyway, linear low has like the regular spacing. Yeah, and that gives you control over the crystal thickness and the melting point. And then low density is the original. So this is made at I think it's made at 150 MPa. Some huge high pressure, like 150,000 atmospheres in a reactor that's like 4 stories high with little windows in it. You can look in and see the polyethylene like snowstorm coming down. So it's the original way they made it. Just pump up the ethylene monomer at super high pressure and just like throw in a little bit of catalyst and it explodes into polyethylene. It comes down to the snowstorm, collected at the bottom somehow. I don't know how they do this. Like they're making like hundreds of train loads a day or something like this. So it's not like a small scale operation. And so anyway, and that process has been around since like 1940 or something, 30 maybe. It's been around a long time. Then linear low came along. Linear low is like a metallocene catalyst. That's kind of recent, like in the 90s. And then high density came along with Sigma in the 50s and 60s. And high density, and then and at the same time, like isotactic polypropylene. And at the same time, like that was a Nobel Prize with that. But right, so anyway, so these are basically film grades, like for plastic film. Like the big problem is a non-reusable film stuff that's blowing around all over the world, basically. Right? And then this is more milk jugs and climbing chairs for kids and stuff like that. And the ultra high molecular weight is the oddball thing. Anyway, so he says they're going to mix, but they don't. Those things don't necessarily mix, you know. Anyway, so and then if you want to mix them, then what? I don't know the answer to this business, but definitely the Deborah numbers, like your process speed. So the material itself has a relaxation time to it. In other words, if you plot the viscosity versus shear rate, then it starts to tail over. It's that time where it starts to tail over. 1 over that shear rate is going to be a time. The units of the shear rate are inverse time. That's a time. That's a relaxation time for the chain. Viscoelastic relaxation. And then so if you're balancing out, like So where is it going to flow easier? So the viscosity drops, it's going to flow easier at the high shear rate. So the higher you shear it, the better it flows, right? So that that tail over is going to happen at a higher, it's going to take longer to relax the ultra high molecular weight than the high density. So it's at different times anyway for the two. So if that doesn't match up between the two, you get the situation where you're trying to mix, say like you're trying to mix molasses into water or something. Yeah, it's going to mix, but basically you end up with chunks of molasses flying around and the water flows like crazy. Right. So the same thing, you're going to have chunks of this ultra high molecular weight like zipping around, and the high density is just like less viscous. So it's not going to mix with it. Right. So you have to figure out, anyway, there's problems with just mixing it and kind of what kind of, so you really want to get this dispersive mixing, not the distributive mixing, I think. So somehow you want to get, and that involves getting the diffusion coefficient so the thing can, so basically this relaxation time to somehow match up and get it to mix in. I don't know. So just say something along those lines about this thing, like kind of, this has something to do with the time of the material, the time of the mixing, and then whether it's laminar flow or turbulent flow, and then like this issue of having two things that have two different relaxation times and how they could mix. That's the theme, and then just write a song around that theme. No, don't worry about what you say, but just kind of piece those things together would be good. Any way you pieced them together would be great. If you don't get it, then that's not that good. Right. So, but basically those are the issues that he doesn't talk about any of those issues, I don't think. Right. He says he used a high shear mixer. I mean, that's kind of like a grunt thing to do. I mean, in other words, it won't mix, so I'm just going to hammer it harder. Right. So that's basically like caveman technology. So this is trying to get at maybe how you might address it a little bit. I mean, the paper is fine, but basically this is something that isn't really addressed in it. And then so he goes through, I think this equation 7, he goes through an exact scheme of how to do that, how to apply it to the data. Like how, so there's kind of a sequence of events and he lists them somewhere in here. So the task for that is to find where he lists them and just kind of put it into your own words. Don't, like, a couple people have been like totally copying things and then just pasting it in, so that it's kind of pointless to do that. I mean, I don't exactly take points off if you do that, but basically that's kind of like, it doesn't indicate like you know anything about it at all. Even if you parrot it back in your own words, that's pretty useful, because at least you're kind of committing to memory or something a little bit. But so anyway, try not to just copy what he said. Try to put it in your own words if you can. If you can't, and you're desperate, maybe it's all right. But it's actually illegal to do that. It's like plagiarism, but anyway. Cox-Mertz is the thing about, he's like, his equations are on time dependent equations, and his measurements are all in frequency. So that you have to make an assumption that you can swap out frequency for time. In other words, if I do a stress relaxation measurement and I get the modulus as a function of time, then I can Fourier transform that into frequency and I get this oscillatory shear measurement from it. And the measurements I make are all convertible one to the other. So that can't be exactly proven. So it's called a rule, meaning that people just assume that you can do that. Right. That's that thing. Figure 8 has a power law dependence 0.7. So this is just, I guess he shows intrinsic viscosity. Oh yeah, here, intrinsic viscosity 0.7. So that's the thing for, this is kind of 1 over C star. That if you, so that's whatever we got for the C star number. For a good, I think for a theta solvent. 0.7. 0.5 is for a theta solvent, 0.7 is for a good solvent. So anyway, so that's just, you can get that by 1 over C star with that scaling relationship. This is against, I think it's against molecular weight, right? So you can get that. Then let's see. this is also just a sequence of events that he gives in the paper. So this is a question, just find it in the paper and put it into your own words, he says. He gives a list of steps to do that. And involving that equation, that parent equation with the blends, whatever, equation 7. So he's gonna somehow Fourier transform that and then fit the data using that equation. I think he shows examples of that in here somewhere. Maybe this stuff somewhere here. Or these are his calculations. Anyway, then figure 9 shows a fraction. So as you add more ultra high molecular weight to the high density, then you get a lesser, like a lower return on it. So it doesn't mix. See, so like the last plot, I guess, this thing. So if you have a small amount of ultra high molecular weight that you mix in, then you almost get the same concentration from this rheologic measurement as you get from what you added in. But as you add more, less of it goes in. Right? Less of it impacts the rheology. So it could just be that it's limited miscibility, and if you have 0% of something, it's 100% goes into solution. Whereas the phase diagrams always end at mixing, right, with a low concentration end. And as you go up, maybe you get a smaller fraction that mixes, something like that, meaning they're immiscible, right? When he goes up to 10%, and he's getting five of it mixed, or maybe 6, yes, but so anyway, there's something to be said about that. He doesn't say anything about it, so he could maybe just say something about it. You might have some other reason why that happens. He claims they're miscible at all concentrations, and I say they probably aren't.
Is that timing for us, right? Kind of part A, sort of?
Yeah, definitely. Yeah. Yeah, like if you look at this seriously, then this one shouldn't be too hard to say. Right? I mean, yeah.
Can you calculate like solubility parameters for these two things? So you might have for like normal solvents and salts, or just a totally different framework for polymers.
Well, I mean, this is a good question. I mean, so this is almost like a phase diagram somehow that he has, I guess. So he's got the fractions. You got two phases here. One's pure, almost pure long chain, and then the other phase is this blend. So you can get the fractions of the two phases. So it means it's in a two-phase region. So you have the 2 points of the tie line. So you have the composition of the base, then you have the amount or something at the other side. You need temperature. So you're at a temperature. So then if you have 2 points, if you have 1 point, you can get the Flory-Huggins analysis get cut. So yeah, if you have 1 point on the binodal line, that gives you the chi parameter. Yeah.
So that graph is at 5 minutes, right? So maybe if you let it go longer, they would be fully.
Yeah, that's true too. That's a pretty good point. Yeah, that's another good point. Both of those are really good points. You should put them in your homework. Like, but yeah, so the mixing time is like if you're talking about processing, it's never finished. So basically, you can't wait forever. So he has to do it at some point. And he does it. Is it at 5 minutes? And
There's 5 minutes per paragraph.
oh yeah, right here. Yeah. So yeah, so yeah, it definitely changes with the time of mixing. I mean, I would think it would. But also the thing about the phase diagram is pretty good. Like if you you have a composition at a temperature, you can get the chi parameter. And then once you have the chi parameter, you can predict the whole phase diagram under those conditions. It's kind of like a kinetic phase diagram. It might change with mixing time. But yeah, that's a pretty good point. He doesn't mention that either. So he didn't really, other than the rheology, he didn't really delve into what answers he has, I guess, even, but it's good paper. I mean, I think it's pretty good. And it's kind of like intended to, the other thing is there a need for higher modulus high density polyethylene? Like what's the need for that? Because we have polystyrene, polycarbonate, and this ultra high molecular weight is kind of expensive, so. Is there really a need? Like he never, at the beginning of the paper, he should have gone into like. What's the purpose of doing this? Like, is it actually a marketable thing? Like, does anybody really need a higher modulus high density polyethylene? Because it's like it's a disposable item, right? In other words, most part, it's not going to be a much of a value added product. It's going to be like a milk jug. So, I mean, maybe you could recycle it, but basically it's not a value added. So, and there are polymers already that have high modulus that are relatively cheap, like polycarbonate or something. So why would you want to go like use this, try to go through this whole process and make this stuff? Like he never actually says that. And is there a market for that? Is there some kind of need? Like that puts this paper into like the general rheology and not into like nature or something. Like there was an actual need and he demonstrated he could do it. You know, then it looks a lot more appealing to people to read it. So anyway, that's pretty good points on that. Any other stuff on this thing? Hopefully it's not, it seems like it would be an easier paper to do, but not necessarily because anyway, the equations are kind of complicated but he went through some rheology things. Hopefully you kind of get a feel for what's going on with that. So, right, that's pretty good. Right, so what I want, I'm back in slides 2C, right? And then I wanted to go through some stuff on scattering from 2C and then jump back to 3 to do the RPA thing. Like, so it's kind of a mixture of these notes. It's not there in sequence exactly. So the first thing is like you want to like we kind of drive like all these things about the chain size and how do you actually like measure it. So then this radius of gyration is the first topic because that's what you can measure in scattering. Because in scattering you're going to do Guinier's law. It's basically you're going to scatter from a polymer. It's got a power 2. That's the dimension. And that power 2 ends when you get to the total size of the thing, which is the coil size. This is going to follow a Gaussian. So on a log, a bell-shaped curve looks like this knee thing, right? And that knee thing follows Guinier's law. So basically, that thing will spit out the radius gyration, right? So radius gyration is something you can easily get from either light scattering or from this is neutron scattering. This is actually just a calculation, but would be neutron or X-ray scattering with that size scale. Anyway, so sorry, this RG thing, so defining it, it's kind of one of the first issues for a polymer chain, right? So RG for a did I believe that? Oh, I got a lot of facts in it. So RG is going to be R squared, and then if you have like a sphere, so say a sphere, and it's 4/3 pi R cubed, and then so this normalizes it, not so you want to get the average R squared. You reduce that thing. And so you have R squared in the probability. See, I shouldn't make it 5 from this. This is 2, it's 4. There, like that. Yeah. So this thing gives you R4. Begin the average R squared. You do the like surfaces of the sphere. Now that gives us this is going to be RG squared. And so the 4 pi cancels. The integral of R of the 4 is R5. Integral R2 is R3 of the 3. You get the 3/5. 3/5 of R squared is RG squared. The average RG squared per sphere. So you're going to do some kind of integration. So the weighting factor is the material, and then R is the position you are in the thing. So you weight it. The weighting factor is like how much of that is as a function of R, and then this normalizes it. That normalizes. You're going to divide by like in polymer chain. This normalization is going to divide by n, like divide by how many chain units. And this integral thing is going to be, well, I'll show you how to do the integral. It'll be a double sum with the integral. So anyway, for a sphere, it's 3/5 r squared, and r being the radius of the sphere. So you can say like we said, the hydrodynamic radius is like the drag coefficient if it was a sphere. So RG also has a sphere equivalent, which would be like 3/5 of the radius of the sphere. Right, so I think it's like it ends up being like 1.75 or something. The RG is going to be smaller than the R. Right. So this is also solid, like a solid object. RG is smaller than R for a solid object, say a sphere, right? But for a fractal object like a Polymer chain, then RG is going to be larger than R. Right, so that's a distinguishing factor. And R, remember, it's like R would be equals RH for a hydrodynamic radius. So if you take like RG over RH, so if RG over RH is less than 1, then solid. If RG, I think they do RH over RG, which one they do. RH over RG is greater than 1, it's a solid, less than 1, it's a fractal thing. So you can do dynamic light scattering measurement at RH, then do the static light scattering on the same machine, get RG. Then by the ratio, you can kind of tell what the thing is in a sense. You can tell if it's solid or fluffy. So anyway, so that's part of this RG thing. The polymer thing for RG is like this. So you're going to take the center of mass. So it's like a moment of inertia, right? Except you're using the mass as the weighting factor of it. You say from the center of mass, which is center of mass is capital G thing, the summation of all the R's. Okay, so what is R here? So let me go back, do that. So we come to the picture of what's going on here. I hope these aren't important notes, but so you have your chain around, it's got monomers in it. And you have some odd point that's like 0, 0, 0. Right? And you have vectors. So Ri is like the vector going to that. So if I sum up all the Ri's and then this n of them, divide by n, then I find the center of mass. So if I take all these vectors and add them up and then divide by n, I'm going to end up with some point that's like center of mass. And that thing would be this big RG. That's the center of mass vector. And if you take the center of mass vector and sum up all the vectors that go to every point in the thing, and then divide by n, then you get and square that difference, because some of the positives and the negative, so you have to square the difference. Then you get small RG. And so that's kind of what's going on here. Needs a little graphic, but right. So these big R's are just some arbitrary point and like origin point, and then you going to have this RG is the center of mass, and then each one of your n things, you're going to sum from 1 to the mass of the thing, divide by n to normalize it. That thing squared, so you get the average, which should be the moment of inertia if this was mass. So they were using like the scattering. It's the same as a moment of inertia for the particle. Right. So if you want to say like, how does this relate to the end-to-end distance, right? NL squared, or R squared is NL squared. Then you need to reformulate this thing in a kind of complicated way. So you're going to plug in that summation into this summation. So we want to get into the form of like n minus m, so like the Gaussian walk form, like NL squared. So that, in other words, between 2 points in the chain, the distance is going to be NL squared. So you want to get it kind of into that form so you can get it into the end-to-end distance. So you do that by plugging that thing in here and then realizing that you can pull this summation out here, right? And then you can, it's a matrix where n and m are the same number that's varying over 2 summations. So you need to divide by 2. So the n, it comes out 2n squared as a prefactor. And then a double sum over n and m of that thing, which starts to look like this n minus m. So then you realize that this part, that summation, not the 1 over 2n squared, but that part is going to be, because it's Gaussian, it's going to be NL squared. And the n part is going to be the difference between the 2 indices. And then b squared is L squared. then you do some math things, like you use this power series progression thing. So you have a summation of powers is this expression. So you can work this thing into a summation of powers by doing a couple tricks. So first you say not n is 1 to n, but n is m to n, because it's a symmetric matrix. So the two sides of it, it's going to be a diagonal across where n equals m, where it's 0, and the top and the left and right, top and bottom are going to be like mirrors of each other. So you take that summation, you convert it into this n equals m, and then you multiply by 2. So the 2 halves gives a whole. And then you realize that when you do this sum, you can rewrite this expression as something like this, like z. So 1 times z, 2 times z minus 1, 3 times z minus 2, blah, 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 to z, right? So this n minus m, that summation ends up being this thing. Then you can convert that thing into this thing, which is going to be a single summation over p. First term, like if p is 1, then that's 0, that's z. And then p is 1, it's 1. So that's just z. And then the next one, where it's p is 2, this is z minus 1, which is that term. And then this is 2, so it's 2 times z minus 1. So this thing works to give you that thing. And this thing works to give you that thing. Right? And then once you have this thing, you pull out a z minus 1, z plus 1, and then you have two summations of this form, like something to the p to the 1, p to the 2. If you plug that in, you'll get this expression, and z is going to be n minus 1, so you end up with n cubed over 6 for this part of the thing's double sum. Divided by n squared gives you n. And this thing, this double sum is times b squared. You end up with b squared. You end up with b, this thing, b squared times n over 6 gives you RG, and this top thing is the end-to-end distance squared. So it's possible to get this relationship that RG is directly related to end-to-end distance, 1 to 1, and there's just a factor of 6 that differs between the two.
Was C the number of like distances that you were going, what number of points?
Z is just replacing like the n here. So z is n minus 1 to get it to look like that. It's just a math trick. It's kind of like algebra, and then this math trick. You can go through this. I'm not sure how much it's worth it, but it's kind of fun. If you like math, it's fun to do. But if you don't like math, I mean, hopefully you can accept that this is true, I guess, at that point. Anyway, this is a standard form. So that's nice because you have a direct measure of the end-to-end distance. Hydrodynamic radius just gives you this fluffy thing, like you don't know what exactly it's equivalent sphere diameter for this coil is floating around. So you say it's the size, but what does that even mean? But this thing actually means something. So RG could conceptually be a very useful number, right? But the problem with it is this, the only way to measure it is going to be with scattering through this equation, right? So if you let me go over here. This is the dirty truth, right? So you have exponential r squared q squared over 3, and then it's n times n, right? So n squared. So like this is how many chains are in the thing, right? And then n squared is going to be the number of, say if it's X-ray scattering, be like the number of electrons in a chain. Right? So that's going to be like the volume times the density. So r cubed squared is r to the 6. This would be the density times the volume. Volume is r, so density times r cubed, and it's squared, so that's r to the 6. I mean, I'm talking about if you have a Pauli dispersed bunch of chains, which you always do, right? Exponential is going to be 1. You can expand that to 1. That's small q squared, which is like where you are to get this Gauss law, because you're at the low end to get this new thing. Okay, so that's a r q is less than 1, like much less than 1. So you can just do the linear expansion of that thing, which is r g squared p squared over 3, right? And if you're doing some probability distribution of that, so you're going to have r to the 6 times r squared is r to the 8. So this thing, if you average that, that's the average r to the 8 power. R squared equals R8, and we normalize by this thing, so divide by R to the 6. So if you have, say you have a distribution, so you have like number versus molecular weight versus R, and it's gonna look like this, and maybe if it's high density polyethylene, it's multimodal, it's got multi-peaks in it. So the mean of that would be like here, like that would be R, average R. It would be like there. Then like average R squared would be somewhere there. Then average R to the 8th is like out here. And average R to the 6th is like here. Right, so you aren't really looking at the RG doesn't mean anything. Like if you have a polyester sample, it's meaningless. It's talking about absolutely the largest thing in the system. Like because you have an 8th moment over the 6th moment, it's like this number divided by that number and the square root of that to give you the RG. Right, so it's nice. So you can say like it's a perfect answer. Your problem of finding the coil size until you get to the idea that everything you have is like polydisperse. So it's an exact match theoretically, perfect match, but the problem is that you got this issue. Right, so there is kind of a way around that. So anyway, so if you linearize. So Guiney's law, you can linearize it. If you do, so we did like with the RPA, you have 1 over I. Like we had 1 over the intensity as a sum of the inverses of everything. So that originated with this idea, the Zim idea, where you have 1 over I, and then this 1 minus for the low Q extrapolation of this becomes 1 plus, because it becomes 1 over exponential minus, it's exponential plus. So when you expand that, you get 1 plus RD squared Q squared 3. So you plot I, 1 over I versus Q squared, and you're gonna get RG as a slope, as a straight line. And then the intercept is going to be the molecular weight. This G is going to have that N in it. So it's going to have the molecular weight of the thing in it. Right. So you can get the molecular weight from that kind of linearization of the Guiney's law, which is basically a Zim plot, called a Zim plot. Anyway, so is that business. Then so there is a way to get a better picture of things. Okay. In other words, since RG for polydisperse systems is going to be bad, so you look at this thing. So you have, say you just have a surface, right? And then you're going to have like things in, and then you're going to have, say you're looking at vector R. So this vector R is this thing here. So it's going to involve like interference between particles. So this is what interference looks like. So you have an incident wave, and it just the peaks. It's going to be a sine wave. So you put any of the peaks black lines, right? And then going to collect the same wavelength, light, X-rays, and neutrons at some angle, right? And then the points where you could generate that scattered wave are where the exiting wave and the incident wave are coincident, meaning the fringe lines. So the fringe lines are where the ones coming in are on top, are at peak at the same point as the ones going out. So if you have material at that point, the incoming wave comes in and it's going to excite the electrons in the material. The electrons are going to jump up and down, and that's going to create, so moving charge makes a magnetic field that makes another wave. Right, so the way this works is coming in with electric field, hopping up and down, electrons get excited, they hop up and down. Then those hopping up and down electrons give off a magnetic field that creates, when it goes down, it creates, at the steepest slope of the electric field, it makes the maximum magnetic field. So it's oscillating between magnetic and electric, right? Normal to each other. So the magnetic's going in the lower plane and the electric's going up and down. Anyway, so basically you need stuff at those fringe points in order to generate scattering at that angle. And those fringe points are separated by a vector R. They're separated by an arrow, right? So it's a vector. So if you change the angle, which I think I can do, I have to enable editing. Do that. Cancel. Cancel. There. So I can change the angle, I guess, for that guy. So you see, if I go to high angle, that thing gets small. Go to low angle, that thing gets large. The direction of it changes slightly too. So if I measure at that angle, I need stuff at those points. Right? And if I'm measuring at this high angle, I need stuff at those points. So if you throw onto that like a crystal, right, then the crystal atoms have to be at those fringe points, and then you get a diffraction pattern going up there. Right. And if I move this thing around, I get no diffraction because it's too big, and then I get diffraction, I get no diffraction. So that would give me a peak. And this is theta going that way, so it'll give me a peak for a crystal. The crystal has to be aligned. It has to be aligned like the way it's shown, you know. Like if it isn't aligned the way it's shown, you get nothing. So if you stick a diamond into an X-ray beam, you get no diffraction from it. If it's a monochromatic X-ray coming in, right? Unless you rotate it until you get exactly that arrangement of a crystal plane, so you get this kind of. So that's why this starts to look like a reflection. It's like if this was an arrow of the beam going in, it looks like it's being reflected off that crystal plane. So sometimes they call that specular reflection, mirror reflection, right? That gives you the bands on it. So that's the idea. You have this vector R here, right? So anyway, so if you have a we're out of time. So anyway, so I'll go on from that. Anyway, we got the vector R. So with the vector R, I can show you some other things about like kind of simple things about scattering. Like in other words, how you can get an actual size instead of RG. That's one of the main themes. But all right, so let me quit there. Yeah. Hopefully, okay. Let's do tomorrow, right? So, right. Good.
Remember that person who talked about it.